Welcome to the third and final in our three-part trilogy on working with measurement numbers. In this one, we're going to look at multiplying and dividing measurement numbers and how to accurately report their level of precision and accuracy. And unfortunately, things get a little different and a little trickier here. It's not as straightforward as adding and subtracting. For one thing, we need to pay special attention to the units of measure and make sure we deal with those properly. And the other thing is the way we round is different than when we add and subtract. Add and subtract was very simple. When you're done, your solution, your answer, needs to be rounded to the least level of precision, right? So basically the smallest level of accuracy, right? If it was accurate out to 2 decimal places was the smallest one, then your answer would be 2 decimal places, even if others went to 3 and 4 and 5, right? Those kinds of things. If one number was rounded to the nearest whole number and the rest had a bunch of decimals, then of course we still have to round back to a whole number, right? It's always the least precise one. Multiplication and division gets a little trickier. All right, so first let's remind ourselves that when we multiply measurement numbers, i.e. things that have units of measure on them, feet, inches, gallons, whatever they are, that we multiply the numbers by themselves, but then we also multiply the units of measure. So you get 3 times 2, which is 6, and then you get a foot times a foot, which is foot squared or square feet. So your answer is going to be 6 square feet. And if there's 3 of them, same thing. Multiply the 3 numbers, get an answer, multiply the 3 units of measure, get now a cubic unit of measure. Now, of course, I glossed over the fact that the units of measure all need to be the same, because how the heck can you multiply an inch by a foot by a mile, right? It doesn't work. You would have to convert them all to one consistent unit of measure. And normally you have to convert down to the smallest one. I mean, you could convert an inch up into a foot, but then it becomes a decimal, and that's a big pain in the butt. So it's much better, and you kind of get a better level of accuracy if you convert everything down, right? So you would take your miles down to feet, and then your feet down to inches, and then of course your miles from miles to feet to inches, right? So everything would get converted down to inches, and you'd have some big ass number in inches when you multiply them. But then when you were done, you could then convert that big ass amount of inches back up into feet or miles, depending on just how big it is, okay? So it's that kind of idea, but you definitely need to have consistent units of measure before you can multiply, and really before you can divide either. So to remind ourselves, right, when we have a linear measurement, it's just a straight line, you know, it's you're measuring a distance. When you multiply those two things together, that gives you an area, and when you multiply them 3 times, it gives you a volume. Now, division. We don't have to worry about units of measure matching up in division when they're singular, because division just becomes a fraction, right? So just like you would divide the numbers, you'd put 24 and you divide that by 1.5. You do the same thing with units of measure. You take miles and you divide it by hour. The only difference is when we talk about miles divided by hour, we use the word per to represent division. Miles per hour technically means miles divided by hour. So whenever you see the word per, or whenever you see a measurement with a per in it, you know, like mph, which stands for miles per hour, or mpg, which is miles per gallon, it just means that, hey, we were doing some division and we had a fraction, and on the top of the fraction was miles, and on the bottom of the fraction was hours, or in the case of mpg, miles over gallons. Okay, so per just means division. Now, I don't like how these slides put this little multiplication in here. We're not really multiplying the number times the units of measure. It doesn't make sense to say 24 times 1 mile gives me 24 miles. Really? I don't know. I mean, it's correct, but it's kind of clunky. Another thing to mention is that sometimes some of your units of measure will be described differently. The standard way in the metric system to describe hours is with an H, because the metric system is all about being precise and simple and clean, so why put an extra R on there? But in the United States, with our stupid non-metric measurements, we normally say hours as HR. So just keep that in mind. You know, if you're ever looking things up or dealing with measurements and you see it listed either way, just know that it's the same. Okay, When multiplying or dividing quantities having compound units, meaning like if you want to do miles per hour times, I don't know, feet per second and these types of things, it gets kind of tricky. But it's oftentimes, not even just sometimes possible, it's oftentimes possible to cancel out units of measure when you're doing division or multiplication, depending on how your units of measure are. So let's look at some examples of that. We're going to multiply 45 miles per hour times 4 hours. Well, we have to remember that miles per hour means miles divided by hours. And then we've got the 4 hours. We can put the numbers together like normal, right? So 45 times 4 gives us 180. But now we've got miles over hours, right? Miles divided by hours times hours. The hours cancel out, and our answer is just in miles, which makes sense, right? If we're traveling at 45 miles per hour for 4 hours, we know that the answer we get is going to be how far we went. So our answer, the unit of measure, should be miles, right? The hours have just canceled out of that equation. If we take 42 square yards, right, an area, and we divide it by a linear measure, shouldn't our answer be linear? Yes, of course. And if we do the simple algebra with those units of measure, we can see how the math works. 42 divided by 6, right? So we put that in a fraction. Square yards divided by yards, we put that in a fraction. And we go ahead and we simplify it, right? Because square yards is just yards times yards, and then you divide by yards. Of course, the 2 yards cancel top and bottom, and you're left with just 1 yard on top. And then 42 divided by 6 is 7, and our answer is 7 yards. Yay, it makes sense, right? Everything works the way we expect it to work. And that's the nice thing about units of measure is dealing with them, they work the way we think they should work. Now, when measurement numbers are multiplied or divided, the resulting answer cannot be expressed with greater accuracy than the least accurate measurement number in the calculation. Just like with adding and subtracting, we kept them to the least level of precision. Here, though, however, we're dealing with accuracy. So that's the big difference between multiplying and dividing and adding and subtracting. With adding and subtracting, we can let it be the least precise number. With multiplying and dividing, we have to go to the least accurate measurement. And if you don't remember the difference between precision and accuracy, precision tells you how far out your measurement goes, right? It's basically how many decimal points you have. What's the farthest right significant digit, right? So if it just stops at a whole number, then you're precise to the ones place. If it goes past the decimal and it goes out, 2 or 3 spaces, then you're accurate to the 100th or the 1000th and so on and so forth. So precision tells you how far right your, what's the farthest right significant digit you have. And then accuracy just adds up how many significant digits you have, right? So we're just looking for the smallest number of significant digits. So at least they both always go to the smallest or the least thing in the group. It's just with adding and subtracting, it's the least level of precision. Multiplying and dividing, it's the least accuracy. Okay, so we multiply these two numbers. Of course, we're going to get feet squared because feet times feet. You're going to do the stuff in your calculator and get 15.66. But if you look at the two numbers, 4.33 is accurate to 3 significant digits, right? It has 3 significant digits, so that's its level of accuracy is 3. However, 3.6 only has 2 significant digits, and therefore it's only accurate to 2 significant digits. So our answer needs to have only 2 significant digits. And because our answer is 15.66, we now have to round down to 2 significant digits, which means we're rounding to the ones place, right? 1 significant, 2 significant. So the 0.66, because this is bigger than 5, the 6 here, this first one, then this rounds up to 16. And so our answer is it's roughly 16 square feet. That's as accurate as we can get because of what we're given. Same thing with division. Miles divided by miles per hour. Well, you got to remember that when you divide by a fraction, you're really multiplying by the reciprocal. You got to flip it. So miles divided by miles over hour becomes miles times hours over miles. And you need to do that because we can multiply fractions by multiplying straight across. So you get miles times hours over miles. The miles cancel, and your answer is just in hours, which makes sense, right? That if you take miles and you divide by miles per hour, you're going to be left with just hours, right? The distance you travel divided by how fast you went gives you how long it took you to get there. But then we also divide the numbers. 375 divided by 65, get 5.7692, blah, 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 right? But the smallest level of accuracy was the 65 miles per hour. It only had 2 significant digits. So the 5.7692 needs to be rounded to 2 significant digits, which means it needs to round to the 10th place, and we get 5.8. So that's where multiplication and division gets a little tricky, is we're not rounding to the least precise number, right? We're not rounding to the lowest level of significant digits. Instead, we're rounding to the lowest number of significant digits. Now, numbers that result from simple counting should be considered exact. They do not affect the accuracy of the calculation. So for instance, if a flywheel turns 48 rotations in 1.25 minutes, then the speed of the flywheel is calculated as 48 divided by 1.25, which gives us 38.4 revolutions per minute. We should assume that the 48 is an exact number because rotations are counted directly. So, right, so we couldn't have like 48 and a half rotations and report it as 48. So it's the big difference between a count and a measurement. If we measured something to be 48 inches, we could be off by, at least a half of an inch because we rounded to a whole. However, if we count how many times something does something, we're not going to go, hey, it went 47 times. Let's just round that up to 48. Hey, it went 47 and a half revolutions. How the hell can you get 47 and a half revolutions? For one thing, you wouldn't count 47 and a half revolutions and then figure out how long that was. You would wait until you got that complete last one and get 48 exact revolutions, and then you would count that amount of time, right? So counts are accurate. And because of that, it kind of lends accuracy to our answer. And so now we can look at the accuracy of the other one, right? So 48 is perfectly accurate. So you can think of its accuracy as being like infinite. But then what's the level of accuracy for 1.25? 3 significant digits. So our answer should be rounded to 3 significant digits, which is 38.4. So even though the number 48 only has 2 significant digits, its level of accuracy is infinite. It doesn't stop at 2. So when we're talking about the smallest level of accuracy, it actually goes to the other thing, which is a measurement, not a count, right? And so we use 3, and so we keep our answer with 3. So this is where these things get tricky, right? Adding and subtracting is really easy because it's just the most precise measurement, right? And then you go to the least precise measurement, and that becomes what you can do. So you look at how precise it goes, which one is the worst, right? Which one has the smallest amount of precision, and that's what your answer should be rounded to. Multiplication and division, it's always the lowest level of accuracy, and if anything is a count, you're counting something, not measuring something, then that's considered to have infinite accuracy. So you look to the other things. You basically only look for the measurements, and then what's the lowest level of accuracy for any of your measurements. Okay, our last example. Each inch of cold rolled steel weighs 0.22 pounds. A certain job calls for 27.5 inches of the steel. How much would this amount weigh? Well, we got to simply do some multiplication. That we get 22 pounds per inch times inches. We see that the inches will cancel and we'll get our measurement in pounds. 0.22 times 27.5 gives us 6.05. 0.22 had the smallest level of accuracy. It only had 2 significant digits. So we have to round to 2 significant digits. So our answer would be 6.1 pounds. I lied. We got a couple more examples. Sorry. Decimal equivalents. So some measurements made by technical workers in a shop are made in fractions, but on many drawings and specifications, the dimensions will be given in decimal form. So you need to be able to, one, convert back and forth, and sometimes you also need to figure out, what a decimal is as a fractional and find like the closest answer to it. So the steel rule used in the shop or in other technical work could be marked all the way down in 1/8, 16, 32nds, or even 64ths of an inch. Heck, I've even seen things that go all the way down to 128th of an inch. A common problem with this is to be able to rewrite a decimal number to the nearest measurement, to the nearest 32nd or 64th of an inch, depending on how accurate your rule is, right? So if your rule goes all the way down to 124th, then of course you're going to want to try, 128th, you're going to want to try and figure out what's the nearest 128th to your decimal number. If it only goes to a 64th, then you're going to try to find, to the 64th and so on and so forth. It's a pretty easy process. So let's say you have to find the fraction to the nearest 32nd of an inch for the measurement 0.462 of an inch. Well, take 462 and multiply it by 1. But instead of 1, we're going to multiply it by 32 over 32 because we want to know how many 32nds we have. When you multiply 32 times 0.462, that gives you how many 32nds, which in this case we have 14.784 over 32. Because remember, if we multiply by 32 over 32, we're just multiplying by 1. So this is still the exact same measurement. We've just changed how it looks. And so now all we have to do is round that to the nearest whole number, and 14.7 is closest to 15. So 0.462 is closest to 15 32nds on our rule, right? So if we had to, kind of use a rule to measure that out, we would measure it to 15 32nds. If we wanted to do the same thing to 64ths, we would just multiply by 64 over 64. It's that simple. Now we can also figure out what our error is by doing this conversion. Because we used 15 32nds, we know that the actual answer we got was 14.784. So we subtract those two differences, and our 15 32nds is actually off by 0.216 of a 32nd. And when you slap that into your calculator, you get 0.00675 inches, and we could round that to 0.0068. So we know that we're off by that much. We're off by about 0.0068 or 68ths, right? This is tens, hundreds, thousands, 10,000s, 68 10,000s, right? Pretty damn small, so pretty accurate. You might ask yourself, why did we round this to the nearest 10,000th? I honestly don't know. I've always thought that the reason why we rounded the nearest 10,000 in this case was because our original measurement was to the thousandth, right? Tens, hundreds, thousands. So our error is almost always reported as the next level of precision. So that's why we rounded to 4 places, right? 1, 2, 3, 4. Let's say we want to change 1.392 to a fraction expressed in 64ths of an inch, and then we also want to find the error. Well, see, I don't like doing it this way, but if you want to just stick with the same recipe is always take your number, multiply it by 1, and the 1 is always going to be a fraction based in the units that you're going, right? So we're going to 64ths this time. So instead of multiplying by 32 over 32, we multiply by 64 over 64. But here's the thing. We really only care about what the fractional part of the decimal part of the inch is. We know that 1 point something is going to be 1 inch and then a certain number of 64ths. So why go to the hassle of multiplying by this, getting a number that's bigger than 1, and then going from there? I instead personally would take the 1 out, multiply 0.392 times 64, right? And then get 25.088, round that to 25, and go, my answer is 25. It basically saves you the hassle of having to go to 89 and then going, oh, take out a 64 and see what's left over, right? It's just, I think it's a little sloppy to not be able to go, oh, well, I don't need to worry about the whole numbers. Because like if this was like 23 point, do you really want to take 23, multiply it by 64, get this big, huge number, then have to divide it by 64, figure out how many 64s come out, and then figure out what your remainder is? No. That's silly. Just do the decimal each time, and just know that the whole number goes along for the ride, right? If this was 1 point something, it's going to be 1 and a certain number of 64s. If this was 43 point something, it's going to be 43 and a certain number of 64s. So that's a much more logical way of doing it. Regardless of how you do it, either way, you can figure out what your error is by doing what we did before of taking the actual measurement that we got and subtracting, what we used for the fraction. Again, in this case, if we didn't have the 1 there, we would have just had 25.088, and we would have subtracted the 25 from it, because remember, that's what it reduced down to, was 25. Either way, you still would have got the exact same answer of a difference of 0.088 divided by 64. Throw that in your calculator, round it to the 4th decimal place, because again, we had 3 decimals here, right? A level of accuracy or precision of 3. So we go to 4 and say that 14 10,000ths. And that, I promise, is the last example. And with that, we finish our trilogy of videos on working with measurement numbers. That's all I have for you. Thanks.